So we are on our second day of chapter 1. So before we were talking about our model of gases, wasn't the kinetic model, which is what we're supposed to talk about now. It was the, what do we call them? What do we call this gas? Perfect gas, or ideal gas, right? And so those gas molecules or atoms consisted of what again, Jeff? What did those gas molecules consist of in that model?
The gas molecule?
Yeah, well, they weren't molecules, they were what?
Atoms?
Mathematical points. Mathematical points in space. So, not very realistic. The kinetic model of gases Kevin? Now what are these atoms or molecules? Can you be a little more specific? Melissa, what? Really, really hard balls, spheres, whatever you want to call it, but very, very hard, rigid, right? Can this stuff bend? No. Can this stuff break? Right? One bad thing, though, is this thing, it can do this. What is that?
Rotate?
Rotate. These magical spheres can't rotate. There's no internal modes of motion. Okay? So that's what the kinetic model of gases is. And they have a mass, right? They have some diameter. There's some size to them. But the diameter, right? The diameter, let's just call it D. The diameter, what does this symbol mean? I'm trying to write it better. You have two less thans written next to one another. What does this part mean? If I had just one of them, you'd say less than. But if I have two of them, you're supposed to say much, much, much less than. That's what it means. So the diameter is much, much, much less than lambda. And here's lambda. The mean free path. The mean free path is the average distance between, what would you guess, Shelby? Average distance between collisions. The average distance between collisions. So that's just, so in other words, they're really far spread apart, right? And they're really, really small. Okay. Since these particles are this way, their collisions would be referred to as what? What type of collisions? Starts with an E. Elastic. The collisions are elastic. So I thought this is kind of neat, so I just want to show you. Well, stop them. Okay. So what I want to do, have them collide. So you got to catch them because they're going to fall all over the place. Get it back. Yeah, Gloriani, be ready. Get your ankle ready. Kick it.
Still hit my foot.
Can you smell it already? That's what I want to get going here. Is oh, I can smell it pretty strong already. I know Eric can smell it. Where's the energy? So the energy's not going into deforming. The energy's going into what? Heat and sound, right? Those are elastic collisions. Again, I said there's no internal modes of motion. That includes rotation, but also includes this. And we haven't talked about infrared spectroscopy yet, but here's an example of infrared spectrum. We'll get into that. That's really PChem 2. But here's internal modes of motion, right? The molecule is vibrating and doing these different types of vibrations in and out of the plane and all these sorts of things. Now, what's not included here is what type of internal mode of motion?
Rotation.
Rotation, right? That's another one. So this kinetic model doesn't take into account any type of internal mode of motion, okay? The root mean square speed, okay. How can you put this in a better word? I guess you could say the root mean square speed is easier to say than what it actually is. What it actually is the square root of the mean of the speeds. Well, that's a lot more English, so they don't call it that. But that's what it is. You're taking the square root of the average of the speeds. Okay. Here's an equation for it. So if it's a speed, Gloriana, what should be the units for this root mean square speed with symbol c? What units should it be? And again, stick in the standard metric unit system. It should be meters per second. Okay. How about this big M? Kelly, what do you think big M is? Yes, it's molar mass. And you look at the periodic table, you get grams over moles. However, is that standard metric units? Has to be kilograms over moles. So when you start using this equation, don't just find the molar mass and use it. You got to convert it to kilograms per mole. Okay? Otherwise, you're not going to get meters per second. There's a T. Well, let's pick the R first. You got a lot of choices for the R's, Melissa. Which R would you probably pick? I don't know if you've had much of a chance to look at the inside front cover on all these different R's. Where are they all? There's a bunch of them. See, gas constant, you've got 1, 2, 3, 4 to pick from. Only one of them is going to work. You guys should be looking at this, because otherwise it's going to screw up all your homework. Which R do you have to use? Oh, you got your cheat sheet to look at, too.
That only has, you see?
Oh, that one has 2. Well, at least, yeah, okay. You'll narrow it down if you use the cheat sheet. She's looking at page 13. Which R would you pick? Why the first one?
Joules,
Has
Kelvin, and mole.
has joules in it. Definitely you should recognize joule as a standard metric unit of energy. So you're going to be picking the 8.314. You have to use that R in this equation. T should be units of kelvins. Good. Okay. We've got the Maxwell-Boltzmann distribution. And let me show you this. I didn't get a chance to scan this, so I'm trying to get this set up so that you don't have to be bringing your book, but I'm not quite there yet. The Maxwell distribution. Oh, I thought there's a more interesting plot than that one. Where did it go? Here, I like this one. So you have the speed on this axis and the relative number of molecules. And it's just, all it is just a population plot, right? What population has this speed? What population has that speed? And it kind of makes conceptual sense. If you have a high temperature or low molecular mass, look how flat and spread out it is, right? There's a wide range because you're, first off, you're at a high temperature, but then you have low mass, so it's all over the place. And kind of have an intermediate plot. If you have an intermediate temperature, maybe room temp or something, and a moderate molar mass. And then the population really sharpens up if the temp is low, there's not a whole lot of energy available, and make things really heavy. The population distribution isn't spread out too much. So the Boltzmann distribution, that's the game it's playing. And you can get the mean speed by just taking, there's your speed. So you have to sum over all these different speeds. What's f of v? The fraction that is going that,
It's going like
going that,
within v.
that v.
Plus dv, yeah.
Yeah, we're not doing diff v. You're right. We're just doing that exact speed.
Okay.
But yeah, so you can get the mean speed by adding up all the speeds times the fraction that are going that speed. Okay. If I think we should, because the homework is going to dig into this. Let's say we have 20 cars going 80 miles per hour north. You've got 30 cars going, let's say 55 miles per hour south. The mean speed would be what? The mean velocity would be what? The mean, heck, we could calculate. Oh, I better not write that because you're not going to know what that means. The root mean square speed. RMS, the root mean square speed equals what? Okay. Let's try the first one, the mean speed. How would you calculate it?
You do 80 divided by 20 plus 30 divided by 55.
Okay.
I mean 55 divided by 30.
Follow the expression. They want each speed. Now we only have 2 in our sum, so no big deal. But we have to take the speed. Well, we can write that down first so we don't screw it up. The speed is, let's just do 80 miles an hour. Times the fraction going 80 miles an hour. That fraction would be
20 out of 50.
20 out of 50. Okay. And then the other one is going to be what, Gloriana? What would be the other term?
20 or 30 out of 50.
30 out of 50.
And 55.
And 55. Okay. So Shelby, what about this whole north-south thing? Remember in physics, didn't we do like a minus and a plus, that kind of thing?
Doesn't matter for speed.
That's it. It's the absolute value of it, or we could put a minus 80 and a positive 55, whatever. But the point is it's speed. You don't have any direction with this. You don't have any plus minus signs. So let's just leave it alone. Don't overthink it. Mean velocity. So Jeff, how would you start this part out? Mean velocity.
Wait, that's all you do for mean
Yeah, and then you get your answer. It'll be mean miles per hour. It's asking for mean speed. Square root mess is root mean square speed.
Oh,
We're not that. Yeah, that's way down at the bottom. We'll do that one last. Who's that? I was picking on Jeff. Okay, mean velocity.
Do 20 over 50 times 80 miles per hour minus 30 over 50 times 50
Yeah.
miles per hour.
Now he's got to take into account, in fact, before we even write these speeds, we should determine what our convention is. Now he said minus the 55. So he's saying the south is,
You have a larger number for your south.
Well, it doesn't really matter. The point is you got to stick with it. You got to stick with north, south. Okay, so south he's saying is negative x. North is going the positive x direction. So you pick a convention and you stick with it. Doesn't matter big or small. You just got to stick with it. So that's what Jeff is he's saying that 55 is negative. So you got to put a negative there, positive there. So I think he said 20 over 50 times positive 80 or negative 80?
Positive 80.
Positive 80. And then plus 30 over 50 times negative 55. That would be the mean, not the mean speed, that's the mean velocity. Okay, one more. Root mean square speed. Okay.
We just take the square root of whatever we got on that first one.
Okay, did you hear what Eric said? Take the square root or whatever you got on the first one. I think the only way I can solve this kind of stuff is if I remember how it's actually defined. I need to take the square root of the mean of the square of the speeds. Okay. So yeah, it's a mean, but it's a mean of the square of the speeds. So what's the only thing that's going to change in this? I just better square what? The square the speeds. That's all you got to do is square the speeds and take the square root of it. So it's Eric was close. You just got to find the mean of the square of the speeds and take the square root of them. See what I'm saying? So the root mean square speed is the square root of the mean of the square of the speeds. So square the speeds, take the square root.
Total answer.
And then get your, so you'd have 20 over 50 times, and you can even put your negatives and positives in there. It really doesn't matter because it's going to disappear on you. So notice how you're going to have a fraction which doesn't have units times miles per hour squared plus a fraction with no units times miles per hour squared again. You add them up, you get miles per hour squared. Oh, sorry, miles squared per hour squared. Take the square root, you get miles per hour. So it works. The units always have to work out. Okay.
If you were, and that doesn't matter since you square them, but wouldn't you use like positive 55 since you're doing speeds?
Yeah, technically we should. Technically we should. We shouldn't have any minus in those because they want speeds. Okay. The mean speed. Now we're going back to molecules and not cars and automobiles. Okay. The most probable speed. Relative speed. Okay, just some different variations. The speed. Relative speed is the speed one molecule approaches another molecule. The speed one molecule approaches another molecule, relative speed. Well, we kind of had this in our concept preview, but just watch your units, right? What's the pi? Is pi, right? Remember that in the concept preview? Okay. So this expression, I think, works. Bless you. When the molecules are identical. Now, I don't know if you remember this stuff, but I guess let me finish this story here. So, if they're not identical, well, what was it? I think that relative speed. Oh, all you do is, it's instead of c bar, yeah. Well, okay, we'll just get this from the book instead of deriving it. We'll get the point across. Okay. There's a little mu in there. And what is that mu? It's this reduced mass. We're used to F equals ma. We're used to kinetic energy being 1/2 mv squared, right? We're used to these single body problems. We're used to that. And n is just the mass of that single body. We're used to that. But what if you had hydrogen atom bonded to hydrogen atom, right? It's not a single body. You can't use m anymore. You have to use mu, reduced mass, okay? And very often one is much more massive than the other one, and this simplifies, and we'll get into that later. But
Is that 8 kT? Or is that in front of the K?
that's just 1/2 mv squared. I'm just trying to...
Over here, on the C row.
Oh, sorry. Yeah, 8 kT over pi mu. And I don't remember if you need it or not. That's why I wrote it down, because I have it written down. So maybe it's just a special case, so that you're aware that this doesn't always work. Okay. But Boltzmann constant, yeah, little k. What's Na? Na. Well, R is that gas constant, but what's Na? Starts with an A. Not Avogadro's number, but Avogadro's number. Avogadro's number. Okay. Collision frequency. Okay. I think units are really helpful. The number of collisions per second. That's what Z is, the number of collisions per second. But you want your units to work out. So where would you get this C bar from, Gloriana? Where's this thing coming from? C bar.
From the mean speed?
Yeah, it's just the mean speed. You got to plug it in, you got to calculate it. Okay. How about that sigma? Kelly, what's the sigma doing in there? What is that? I think there's, again, I didn't scan this part. It's on, I thought I wrote it down somewhere. Page 29, I went too far. It's on page 29. They call it the collision cross-section, sigma. So it's just the size. You were talking about collision, so you want to know how big things are, and that's going to be a factor in the expression. And it's in the, it makes sense that it's in the numerator, right? Because the bigger something is, the more collisions you should have per second. It shouldn't be inverse, it should be bigger. So it's directly proportional. So that sigma is the cross-section. So C bar, Gloriana, and we already talked about the units. Make sure that's all right. What should this one be in? So you look at the table, right? Oh, the problem is dealing with methane. So you got to find, oh, I guess a table has methane in it. But if you look at this table, all right, it's got a table of all these sigma values. And up in the upper corner, it has this. And this is how this author does, and he's got all his numbers. And he's got his gases, all right, whatever it is. He does this all the time. And it's kind of nice once you get used to it. It says, this is your table of all your sigma values, cross-sections. But they're all in units of what? Nanometer squared. That's what he does it. So it doesn't mean that these are in units of per nanometer squared or anything like that. This is just his way of saying sigma, and it's in units of nanometer squared. Okay. So I guess you could set this number equal to that, and the nanometer squared goes over there maybe or something. I'm not sure. But that's the thinking. So you get, if you want to do a homework problem, calculate the collision frequency involving methane at room temperature or something like that, you have to look up the little sigma value. But can you plug this number directly into this expression? Has to be in meters squared. Now what's nano? Shelby, what's nano? Yeah, good. All right, so nano's 10 to the negative 9, so you have to square that. Okay, so this needs to be meters squared. P. P, Kevin, is probably what?
Pressure.
Pressure. A lot of units for pressure, but only one will work. Pascals. Oh, what's a Pascal? The problem's in ATMs. I got to convert. Just look at the inside front cover. Or look at the cheat sheet. Right? There's your conversions to go from atmospheres to pascals, or millimeters of mercury, or torr, or bar. There's a lot of units for pressure. You have to be in pascals. K is probably what? Melissa? Little k. It's a Boltzmann constant, yeah. And what it is, look at inside front cover, right? Or multiply, divide R by Avogadro's number. T had better be in Kelvin. It's not so bad. Okay. And we already kind of talked about mean free path, but you can calculate it for any gas at any temperature. What's the average distance between collisions, right? Just divide c bar, that relative, what do we call c bar? Relative speed? Mean speed. Divide the mean speed by the collision frequency. And we'll get our mean free path. Okay. So we've got some time to knock out the homework. In the past, folks have had trouble with this thing first, so I say we just set up this problem 1.12. But I think since they've had so much trouble with it, that's why I did this example. So I don't think you're going to have any trouble with it, because you just follow the exact same idea. But let's just set it up. Problem 1.12. So they're not going north and south, they're going east and west. Do you see how it's trying to say this? Right. Yeah, whatever you want to do it. Yeah, you need to decide.
And the number in parentheses, that's how many? So
Yeah.
we need the total.
Yeah, cars are in parentheses. So I think Shelby wanted to do east is positive, west is negative. I think that's very conventional, right?
Total is 328.
So if you're not so sure how to set this up, just let me help you out. So for the first one, we're looking for the mean velocity. I think Eric was nice enough to tell us that total. I think you said it was 328? So like for the very first term, there's 40 of them, right? And they're going east, so that's positive. 80, what other units? Kilometers per hour.
328.
And you just keep going. Do that for every single term. Right? And they take the plus or minuses in there. Because it's velocity. They want mean velocity. So you have to take into account the mean velocity. The speed is going to be part B. Just erase the signs. Erase the negatives, I guess. All right, you see what's going on? Well, you can, but it's all right here. So it's kinda, I would just start with it. And just dig the stuff out of there as you need it. You should bring paper. Now you got to rewrite the whole thing.
Where's that?
You do it all over again.
Really? Suppose since I'm paying you anyway. All right, so I think this isn't so bad, right? You want to go on to the, you see what to do? Kelly, you see what to do? No? Okay, so like mean velocity, what we're going to do is get the fraction and then times the actual speed. And do that for, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9 terms here that we're going to be adding up. Do that for every single one. And then, I forget, I think Shelby said, if it's going west, make it negative. If it's going east, make it positive. So we'd have 40 over 328, 62 over 328. That's going east, so that's positive too. And just keep going. I think the complicated one is the root mean square speed, but even that's not so bad. Just have to square the speeds.
Did you get the velocity? Or negative 2.63. Where's your...
Hold on. I think I have an answer here. I had 2.82
You got it.
positive east.
You write it out? Or do you just do it?
I just wrote out 1 and then from there I kind of just
Okay. I probably like wrote something down.
All right. I can give you the answers for them all. The mean speed, I got 86. All right. No plus or minuses. The root mean square speed. I got 86.2. So those are the final answers. Yeah, so you keep going, and then if it's going,
Oh, I have to change
you have to change the sign if it's going west of the speed. Change the sign, make it negative. And then when they want the mean speeds, you just make all the signs positive, because there's no direction.
like how we
Yeah,
Oh,
when we
then
did the
it's
mean
positive.
speed, all the signs are positive.
And then this one
You keep them for mean velocity. And the root mean square speed, you're doing the exact same thing, except you're just squaring the speeds now. Oh, and don't forget to take the square root of the whole mess.
For this one, we
Let's
keep.
put in like the second.
You
What
can.
it is.
It doesn't really matter because you're squaring it, so the sign goes away.
Oh, no, for that, for this part.
For the mean velocity, yeah, you have to have the sign because velocity gives a direction. Okay, so you have an idea, right? Let's see if we can jump down to the next one. 'Cause I don't know, because there are some little things that see if you don't remember, you're not going to remember. Just going to have some trouble. For example, like calculating the mass of a single atom, right? If you remember how to do it, you're not going to have any trouble. But if you don't, then so determine the. I mean, if you want to wrap it up, we can do that. But since you guys are so deep into this, do you want to finish this
Which one?
and then go on to the next one?
1.13, yeah.
Yeah.
Did you guys have the next video?
I mean, you have time. Once you get it, then jump on to 1.13a and then. If you push hard enough, it erases. Oh, God. Really bad. There's gotta be an easier way to do this. But whatever, if it comes out to be negative, that's fine. That means the mean velocity is net in the negative direction. So just take this time, right? This times that fraction plus that times that fraction. Just add them all up. And if you get negative, get negative. Right?
If this is negative, that's just stays.
Yeah, right. It's plus this sum plus that sum plus. Let's see if you get started on this 13 here. So in 13, part A, they want the ratios of the mean speeds and then the mean kinetic energies, okay, of these gaseous hydrogen to mercury atoms. They want the ratio of it. So what's the variable for mean speed? What symbol did we use for that? C bar. So they want C bar for H2 divided by C bar for Hg. That's part A. Okay. And then in part B, what they want is they want the mean kinetic energy of gaseous hydrogen molecules, for example. Okay. Kinetic energy was 1/2 mv squared. Okay, so let's make it for hydrogen. What little subscript, where else do I put a little H2 subscript to make sense out of this? And the mass. So that's going to be the mass of exactly what? The mass of a molecule of H2. That'll be mass of a molecule of H2. How about this V? What's that going to be? The numerator, the part that you got from A. That will be this top one. Okay? So just a couple tricks to do this then. And the kinetic energy of the mercury, exact same format, but let's just wrap this one up. How do you find the mass of a hydrogen molecule?
You add either two times the molar mass.
Oh yeah, so Eric's saying find the molar mass of hydrogen in the first place. And H2 is, H is 4, where is it? Oh, there's 1.0079. So take it times 2, because he says it's H2, right? And then divide it by Avogadro's number. Okay. Are you done? No. You also have to
Divide by 1,000.
get it into what units?
Kilograms.
Kilograms. Well, the moles kind of gone. You divide it by Avogadro.
Oh, yeah.
But so find the molar mass, right? Divide it by Avogadro, get your answer, convert to kilograms. Otherwise, you're going to be off, right?
What is Avogadro's number?
6.022 times 10 to the 23rd.
Negative something?
Mm-hmm. Oh, no, 6.22 times 10 to the 23rd. Hmm?
Moles per gram. The Avogadro something.
Molar mass is 1.0079.
Right, but what's the units for Avogadro?
It's per mole.
Per mole.
So you have grams per mole in the numerator, per mole in the denominator, so the per moles cancel. So you end up with just grams. So that's why the only last step I had here is convert those grams to kilograms. And to get part A, pretty much just use that equation, right? Plug and chug from that equation.
Then we have to get it in kilograms per mole.
Exactly. Don't forget. In that equation, to calculate mean speed, like Eric's saying, C bar, it's got big M in it. But it's not just molar mass. It's molar mass in kilograms per mole. Exactly. So there's a number of places you can screw up doing this.
Which one were you talking about right now?
Well, for part A. For part A, you need to use C bar is 8RT. I'm just copying it from the notes here. Over pi times M. And he's saying, okay, if you want to calculate the average speed for H2, this has to be the molar mass of H2, but in kilograms per mole. Remember that? And then you got to do the same thing. So get that number, do the same thing, find the mean speed for mercury. Do the same thing. And then divide the two, right? And get your ratio. And mercury isn't diatomic, mercury is monatomic. So when you calculate the kinetic energy for a mercury atom, right, just with the mass of a single mercury atom, you won't be multiplying by 2 or anything. It's just Hg in nature.
Maybe they get the mean speed. Yeah.
There we go. Get rid of this.
Did you get this? Oh, yeah. If you haven't been used to it, you can have it.
So you guys see what's going on here? Did I lose you?
How will we find the mean speed?
The equation, right? Because you're going to have that cheat sheet. And what might be a good idea, you know what, is to have this thing torn out when you're doing the homework. Because you have this torn out when you're doing the homework, then if you're trying to do a homework question and what you need is not on here, you know then it's something you got to know. Right? So if you're looking on here, trying to use this sheet, you have to know that C bar is mean speed. So this would be a really healthy thing to have because it's going to force you to know everything. You'll be ready for the exam if you do your homework this way.
R do we use? The 8.3?
Has to be the one in joules. Yep, metric R. Oh, it's 10:02. Jeff wants to be here all day, but I think we got to kick you guys out. Just get rid of that iPhone. It's junk. It's garbage, I tell you. Garbage. No.
You couldn't handle it.
Oh, I got rid of it. This
Because you had the 5.
$40. It can do everything that iPhone can do and better.
Doesn't have Siri.
Yes, it does. Google's Siri is much better than Apple's, hands down.
I don't like Siri.
But
You know, when you're talking, does the spelling. That's Siri, right?
I don't even use it.
Right? I forget I have it.
And then you have the Google Talk and everything. Everything's Google.
Because you talk out your text messages, right? Is that why?
Yeah, that and talk the web searches, all of it.
Oh, yeah.
And then you know what happened with Apple and their bloody iCloud. All those poor stars that are. Why would they take dirty pictures of themselves in the first place and put it on the internet? I mean, yeah, it's an iCloud, but it's still internet. How stupid can you be?
You can't do it from the cloud.
Jeez. Oh man, I should have stopped this recording for that.